Okay, so we finished up by making this connection between linear equations, systems of linear equations, and matrix multiplication, right? Matrix multiplication, and then we also made this connection between having solutions and the idea of span, right? Everybody remembers span? So linear combinations and span, those are things that are going to be really important later on. So the last thing we finished up with was saying that AX, recall where we finished, we said that the system AX equals B has a solution is the same thing as saying that, what? Can anyone remind me? Can anyone say it in terms of the language of linear combinations or of span? Read?
So bold B is in the span of the set, like bold A1 through bold AN.
Right. So, right, that B is in the span of the columns of A, or equivalently, B is a linear combination of the columns of A. Okay. And so that's the last thing. That's the last thing that we said. Okay. And in fact, I think the book calls this a theorem. Okay, a theorem that for this system to have a solution is the same thing as saying that B is in the span. Okay, which by definition is the same thing as saying that B is a linear combination of the columns. Okay, so that's what we finished up. We're going to sort of ignore that. We're going to ignore that for now and backtrack slightly to the notion of matrix multiplication. So 1.4 is basically more about matrix multiplication. More about matrix multiplication. Okay. So let's recall that if you have a matrix A whose entries are denoted, with little a's, an n by n matrix, and you have another matrix B who's, again, as usual, our convention is always going to be like this, right? Capital B's entries are denoted with lowercase b's, an n by s matrix. Then the product AB is the m by s matrix with ijth entry being what? What's the ijth entry of the product? Zn. How do we find the ijth entry of the product matrix?
If
you take
bold A with the ith row of A and then the dot product with the B column, the j column of B. Right,
exactly. Being the ith row of A dotted against the B. The jth column, the jth column of B. In other words, i.e. Summation aik bkj as k ranges from 1 to n. Okay, right. That's what right. You take the dot product of the ith row against the jth column, the ith row of A against the jth column of B. Okay. Yes, you should all be nodding. I'm worried that you're not nodding. Yes. Okay, so, okay, and we saw that we don't have a commutative property, so we do not have AB equals BA for all AB matrices. Maybe I should say, we do not have a commutative law. Commutative law. I mean, it could turn out by chance that AB equals BA for some matrices, right? That you could luck out, but that's not guaranteed to happen like it is with numbers. Okay, so so although we don't have a commutative law, we actually do have some. We do have, however, some properties. Okay, and so first off, if you're adding matrices, if you add them in one order, doesn't matter in what order you add them, right? So there is a commutative law for addition. Similarly, for addition, you do have an associative law. For matrices, we don't have a commutative law, but it turns out that we actually do have an associative law. So AB times C is equal to A times B times C. Okay, so we don't have to, put parentheses on this. We can just write it as ABC. Okay, so there is an associative law. Okay. Other laws that hold, well, we do have a distributive law. A times the sum equals A times the sum of A times the summons. Okay, so A times B plus C equals AB plus AC. And of course, we have the other way, A plus B times C does equal to AC plus BC. And then we have some sort of dumb rules about constants. If you have A, B constants, alpha and beta, which are constants, so alpha and beta are just numbers. AB times A is the same thing as A times beta A, etc. So this last one I think is not really worth talking about. It just says that you can pull out constants, right? So what? Okay. So right. So we've got these are addition, right? Commutative, associative, right? This is multiplication. We have associativity, and then we have addition and multiplication together. That's distributive property. Right? Okay. So these things, if you're thinking of your matrices as some sort of generalized number, well, we don't have commutativity for multiplication, but we do have all this other stuff. Okay, so just think, if I had numbers, I'd want them to do this sort of thing, right? I'd want to be able to switch the order when I add. I'd want to be able to. I'd hope it's true that I have associative property, etc., etc. We don't have a commutative property, but these other things do hold. Any questions? Any questions? Okay. Okay, so we're going to use this set of properties as just practice for learning how to do proofs. Okay, learning how to do proofs and learning how to write proofs. Okay, so let's show how does one prove these facts. How does one prove these facts? Okay, so let's start off with the first one. So number one says claim one says if A and B are of the same size, then A plus B equals B plus A. Okay. Right, to spell it out a little bit more, right, we can only add them if they're the same size, right, so they better be the same size. Okay, so let's prove it. Okay, so, so just to be kind of pedantic about it, how do you show that that matrices are equal? Do you remember our definition of equality? This is not going to be particularly exciting, but we'll just do it as an example. Yeah, we go ahead.
They're the same size and all their entries are equal.
Right, they have to be the same size and all their entries have to be equal. Okay, so we need to show, one, same size, and two, all entries equal. Okay, so you say, okay, one, they're definitely of the same size, right? A plus B is an n by n matrix. B plus A is also. Right? So it's obvious, right? So one, it's sort of obvious. Right? By definition, when we add two matrices of the size, we're going to get a matrix of that size. Right? So they're the same size. Right? By definition, when you add two matrices, you're going to get a matrix of that size. Okay? So that's you just need to say that. Okay. Part two, I want to show that all the entries are equal. Let me write it this way. Let C sub ij denote the ijth entry of A plus B. Let gamma ij denote the ijth entry of B plus A. So let Cij denote the ijth entry of A plus B. Let gamma ij denote the ijth entry of B plus A. Okay. By definition again, by definition of matrix addition, Cij is what? Cij is the ijth entry of A plus B. So what's the entry? Aij plus Bij, right? Aij plus Bij. I guess I should have. I mean, so we have this convention, right? This is the ijth entry of A. This is the ijth entry of B. I'm not going to say that every time. By definition, this is equal to that. Gamma ij is going to be Bij plus Aij, right? Right, and since scalar addition commutes, right? Since these guys are numbers, right? Scalar addition commutes. These are equal. Okay, so you use the commutativity of numerical addition to prove the commutativity of matrix addition. Okay, right. The entry-wise commutativity gives you the matrix-wise commutativity. Okay. So this is like a very, very simple proof. Okay, and so you say, okay, I've proven what I want to prove. People usually put this thing. It's called the Halmos tombstone, after the guy who first started using this notation. I don't know if Halmos is still alive, but I expect if he is dead, his tombstone is probably a Halmos tombstone. Okay, actually, the first book that I used in college was by Ramos, a linear algebra textbook called Finite Dimensional Vector Spaces. It had no matrices in it, as I recall. Or maybe it had, I think there was matrices on one page or something like that. Okay. Okay, everybody's seeing how you write a proof? Okay, so you say, okay, what do I need to show? I need to show that they're the same size and that all entries are equal. And then you basically go back to the definitions and show that those things are satisfied. Okay. Okay, well, let's do some more examples. To give you some sense of what's going on. Okay, so proof of 4. Okay, so let's prove the distributive property. Okay, so again, let's let D denote A plus B, A times B plus C. Let E denote AB plus AC. Okay. And again, we want to show that the corresponding entries are the same. Okay, I'm not going to worry about the sizes. Proving the sizes are the same is easy. Okay. So I'm just going to do we're just going to do the entry equality of entries. Okay. So take a minute or two and see if you can write down what these entries are. What's the ijth entry of D? What's the ijth entry of E? Okay, write them down, and you'll see that they're the same thing. Okay, see if you can write it down, just to practice if you understand the notation, basically. Okay, take 1 or 2 minutes and see if you can write it down. I'm going to go walk around outside to make you feel more comfortable. Okay, talk to somebody nearby. Talk to somebody nearby, and see what they wrote down. Avery, why don't you move up a seat, then you can talk with Stella rather than sit all by yourself. It's up to you. You can stay back there if you like.
So we're saying that there's no and then
Yeah, but even if the sides split up, we don't just
the summation
times. Like when you mention one, matrix, you have to do the like dot product.
I don't know how to denote.
Okay. Okay, so I guess we actually probably do need to say something about the sizes. Okay, so let's let these guys, let A be an n by n matrix, and B and C be both n by n matrices. Okay, because we're going to need to write down some summation or something like that. Okay, so, right, so what's this going to be? What's Dij going to be? Well, it's going to be the ith row of A dotted against the sum of the jth columns of B and C, right? Right. Right. If you want to spell it out more, it's going to be summation AIK BKJ plus CKJ, as K ranges from 1 to n. Okay. What about here? EIJ is going to be alpha I dotted against beta j. I'm sorry, A sub I dotted against bj, and AI, the row AI dotted against the column cj. Right? Which is summation AIK BKJ as k goes from 1 to n, plus summation AIK BKJ CKJ as k goes from 1 to n. Okay, but that's the same thing as summation AIK BKJ plus CKJ as k goes from 1 to n. Right, by the distributive property. Right, because AIKB times this is this plus this plus this, right? AIKBK, this is the same thing, of course, as AIKBKJ plus AIKCKJ, right? By the distributive property of numbers. Okay, and so you see that those are equal, right? So we're done. Yeah, Hannah.
Can you explain, like in further detail, why D and B are equal to what they are?
Why D and E are equal to
The second part, like what you experienced.
So we're trying to show the distributive property, right? So we're trying to show that this is equal to this, right? Well, to show that two matrices are equal, we need to show that their sizes are equal, which I'm going to ignore. It's easy. And we need to show that their entries are equal. Okay. So this is the ijth entry of D. This I'm using to denote the ijth entry of E, right? Okay. Now, what's the ijth entry of D? Well, D is A times B plus C, right? So it's a product, right? So when you multiply two matrices together, how do you get, right? If you have one matrix times another matrix, what's the ijth entry? Well, the ijth entry is going to be the ith row of X against the jth column of Y, right? So I take the ith row of A, and I dot it against the jth column of B plus C, right? Well, what's the jth column of B plus C? It's the jth column of B plus the jth column of C. Is that clear? Okay, great. Okay, and similarly down here, the ijth entry of E is going to be, well, it's going to be the ijth entry of AB plus the ijth entry of AC. Okay, is that part okay? Okay, great. Okay, so then the rest is just seeing that this works out. So just working through the notation, right? This is the same thing as this. Is that okay? Okay, and this is the same thing as this. That's okay. Okay, so what we have is summation AIK BKJ plus CKJ, right? From 1 to n, right? But you think about that, what is that? That is AI1, oops, AI1, let me, that's the same thing as summation from k equals 1 to n, AIK, oops, AIK BKJ plus AIK CKJ, right? Right, just by, these are numbers, right? So, 5 times 6 plus 7 is 5 times 6 plus 5 times 7, right? Is that all right? Is that right? Just the distributive property of numbers, right? Right. This is definitely equal to this, right? You've done this since childhood. Okay, so so I'm taking the sum as k goes from 1 to n of all these things here, right? Okay, well, I can split this into two parts. K goes from 1 to n. It's these guys as k goes from 1 to n, plus these guys as k goes from 1 to n. Right? Because I'm taking the sum of this plus this as k goes from 1 to n. That's the same thing as if I sum these guys, I add up these guys first, and then I add up these guys next, and then I add them all together. Right? Okay. But what is that? That, we see, is EIJ. Right? That's EIJ. Okay, so DIJ is EIJ. Okay, so D and E are equal entry-wise, right? So, so they're equal entry-wise, and so they're the same matrix. Okay, is that right? Okay, great. Yes, Russ.
I don't think we should use like summation here because the summation, both summation are equal doesn't mean that every single entry is equal. So yeah, I think we should like use like prove every single entry is equal, but not instead of proving that like the summation is equal.
We are showing every entry is equal.
Yeah, but you use the summation like mark, so which is like I don't think we should use that.
Why not? Because the entry is defined in terms of the summation, right? This entry is the dot product of this vector against this vector, right? So it's a summation. It is a summation, right? This entry, right? This is a product matrix, right? So the entry is the dot product of the ith row of A against the jth column of B plus C, right? Which I can write like this, or I can write like this. It's the same thing, right? The dot product of A, ith row of A against the jth column of B plus C. In other words, this.
Yes, but so for the dot product, we get a number, right?
You get a number that is the result of a summation.
Yeah, but summation. Does summation mean like adding the number together?
It means so like right. I have some matrix A, A1, 1, A1, 2, A2, 1, A2, 2. I have some other matrix B, B1, 1, B1, 2, B2, 1, B2, 2, right? Then the product, right? Well, this is going to be A1, 1, B1, 1 plus A1, 2, B2, 1. Right? This entry, right, there are going to be 4 entries, and they're each going to be summations, right? This is going to be summation of A1, I, B, I'm going to use a K since I use a K over there. A1K, BK1, as K goes from 1 to 2. Right? It's a summation. I have to use a summation. Is it okay, Ross?
Yeah.
Yeah? Okay, good. Other questions? Okay, so, right, so this is the second example of a proof, right? We're proving the distributive property. Again, you just go down to the definition. How do you show that these two matrices are equal? You show that they're the same size and that the entries are equal. Okay, so they're definitely the same size, and then we've just shown by this calculation that the entries are equal. Yeah, Nico.
So I think maybe what were you asking that like that's like showing it? It's just showing a summation that like each piece of it is a result of a summation. Like when you have
Yes.
this final notation,
Yes.
and it doesn't mean anything about adding all of the like individual pieces of the matrix together.
Well, what we see is that each of the entries of the product matrices are equal to each other, right? Each of the entries are equal.
Okay.
We're proving it entry by entry, basically.
Okay.
Yeah.
I think maybe that's what were you saying, because like if it were adding together multiple entries of it, then like
that's
we
why-
couldn't know that they're individually the same. Okay. So he was, I think, saying like, how can you know that they're both the same if that notation is showing that you're adding entries together? But you're saying that that's not showing that, that's just showing that any entry is a result of these different summations of the parts of it, and that one entry is the same as the other.
Yeah.
They're the same result of the same type of summation.
Yeah. So let's talk about it after. Okay, let's go on to the next example. I don't want to use it more. Let's go on to the next example because we have to. And we'll talk about it after if people are confused. Because I am confused. I'm not exactly sure what you're saying. Okay. Okay, so the last one is the most complicated one, proof of number 3. Sorry, I'm running out of ink here. Okay, so number 3 is the associative property, right? We want to show that AB times C equals A times BC, right? This is the hardest. Or it's not. It's in fact no harder than the others. It's just a little bit more intricate. Okay. So again, we need to put some sizes on these guys. So let's say that A is m by n. Let's say to make this work, A is m by n, B is n by r, and C is r by s. Right? That has to be, otherwise we can't multiply, so they have to be some sizes like this. Let D denote the product AB, let E denote the product BC. So, and our goal is we want to show that DC is equal to AE. Right? That's our goal. AB times C is the same thing as A times BC. I see I'm just making the board blacker, just distributing the blackness. Yeah, we need a new eraser. Okay, so just as before, we're going to look at entries. Okay, say well, let's just look at the entries. The ijth entry of BC is summation DIL CLJ, as L ranges from 1 to R. Right? It's a dot product of the ith row of D against the jth column of C. Right? Okay, that's what matrix multiplication is. Okay. And so let's expand that out a little. DIL, right? Remember what D is? D is AB, right? So DIL is going to be, so hold on. L goes from 1 to R, CLJ here. So I'm just going to write, I'm going to expand out what DIL is, right? So DIL, well, that's going to be the sum of the ith row of A dotted against the lth column of B. Okay, goes from 1 to n. Right? Okay. And similarly, the ith entry of AE is, well, it's going to be summation AIKEKJ as k goes from 1 to n. Right? You take the ith row of A against the jth column of E. Right? Okay. And again, let's expand what that product is. So we get k goes from 1 to n, AIK times summation E is B times C, so we get BKL CLJ as L goes from 1 to R. Now, by the distributive property, we can put this thing in there, right? This is summation from L from 1 to R, summation K from 1 to N, AIK BKL CLJ, right? And similarly, this one's going to be summation K goes from 1 to N, L goes from 1 to R, AIK BKL CLJ. By the distributive property, right? This number times the sum is going to be, I can sum these guys times that, right? It's just the distributive property. Okay, so we have these double sums, right? One goes from L goes from 1 to R, and K goes from 1 to N. This one, K goes from 1 to N, and L goes from 1 to R, right? But the order doesn't matter. The order doesn't matter, right? We can switch the order, right? You're either summing, first across rows as you go down columns, or you're summing down columns as you go across the rows, right? So it doesn't make any difference, and so these are equal. So these are equal, and so, right, so in fact, DC is AE. In other words, ABC is ABC. Okay, any? Everybody all right? Any questions? So all this is just sort of, can you work with the notation, right? Can you work with the notation? It's not, I think these proofs are basically, do you understand the definitions, and can you work with the notation, right? So, maybe it seems kind of alien to you, but you'll become more familiar with it, and then it'll become easy. Okay. So don't worry, if it seems like, whoa, where did that come from? If you, in hindsight, you'll say, oh, that was just messing around with notation. Okay, yeah, Julia.
I'm confused
Yeah.
because C is R by S.
C is R by S.
We would find C as an R by S matrix, but
Yes.
I would expect to use S in the proof then, right?
S won't show up, just like M doesn't show up,
Okay.
right?
Oh, yeah, okay.
Right?
Yeah.
Because we're multiplying this times this. The index is going to be going from 1 to n.
Okay.
Right? When we multiply these guys, we're multiplying these guys. The index is going to go from 1 to r.
And we use L because we need a variable to define.
That guy that goes from 1 to n.
Okay.
Yeah, we're using L to denote the index goes from 1 to n. We're using K to the index that goes from 1. Wait, the other way. K goes from 1 to n, L from 1 to r.
R. Okay.
Yeah. Good. Good. Okay. Everybody all right? I hope you're not down or anything. Don't get down. Don't be depressed. Hang in there. It's okay. Yeah. So don't worry if things seem completely alien. That's fine. Okay. That's normal. You'll get used to it. So when I first took my linear algebra course in college, I did not understand a thing that the professor said in class, and I went to see him in his tower at the edge of campus. So all the professors all the math professors lived in a tower on the edge of campus, and you had to go trudge across campus to the tower, and you take the elevator and walk up the many stairs to the 8th floor where the professor was. And I walked. It was completely silent. The tower is silent. The great mathematicians are working inside. So I went in and I said, "Oh, professor, I don't understand anything." And he said, "Don't be discouraged." He said, "Don't be discouraged. When I first looked at a theoretical math book, I could not understand a thing." And that was enough. So then I went back to the library and just kept on working. So anyway, so don't be discouraged. Yeah. Okay, so okay. We have a few more minutes. We can talk. But a couple more things. So we've got multiplication down. Multiplication has all these, multiplication and addition satisfy all these nice properties. One thing that we haven't mentioned is, what about the number 1, right? The number 1 has the great property that when you multiply anything by it, nothing happens, right? So we want something like that for matrices, okay? Right, we want a multiplicative identity. It's the analog of 1. And I should say that I didn't realize that at the time, but that professor turned out to be, somebody whose fame will last for the next 1,000 years of human history. It was Andrew Wiles who later proved Fermat's last theorem, a theorem that had withstood, the attempts of mathematicians for, over 3 centuries.
I saw a documentary on.
I'm sorry?
I saw a documentary on.
You saw a demo? Yeah, I'm not surprised. Yeah. So this is Wiles, and if Wiles, so in hindsight, this is very encouraging, right? Because if Wiles, who, like I said, whose fame will last to the end of human existence, was confused when he first saw a theoretical math book, it's fine to be confused. It's more than fine. Okay, but I didn't make that connection at the time. He hadn't proven. I mean, I didn't know how great a person he was as a 18-year-old. Okay, so we want a multiplicative identity. In other words, a matrix. A matrix I such that IA equals AI equals A. Okay. Some of you may know what it looks like. What does the identity matrix look like? Yeah, it's got, well, it looks like it'll be a square matrix, right? So it'll be a square matrix with ones down the diagonal. Okay. I is a square matrix with ones down the diagonal and zeros everywhere else. I'm just going to write a big 0 here and here. Okay. So it's a diagonal matrix, ones down the diagonal and zeros everywhere else. Okay. And you see what happens, right? If A is, say, A11, A1n, A21, A2n, dot, 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 AM1, AMN, then when you multiply, then A times I is going to be A11, A1n, A21, A2n, AM1, AMN times 1, 1, 1, 1, 1, 1, 1, zeros, right? Where this one was an m by n, this guy is an n by n. Okay. Right, and you see what happens? You're going to get an m by n matrix. You're going to get an m by n matrix, and you see what the entries are, right? It's going to be A11, then A21 here, right? If you like think about the first column, right? I'm going to just get the first column of A, right? And I think about the second column, I'm going to dot against the second column here, so I'm going to get the second entry, A12, A22, AM2, etc., etc. So I get A back. Yeah, read.
So for numbers, there's only one identity number, which is 1 for matrices. Is it possible to have like multiple matrices that will give you the same thing when you multiply them together?
This is the only one. This is
Okay.
the only one. Yeah. Now the thing that's a little bit funny about it. One thing that's funny about it is that it has to change size, right? If I'm multiplying on the left-hand side here, I have to use the m by m version of I. Right? It doesn't make sense to, so when you write I, A, this I is actually different from that I. Okay, so you have to, when you see this I, you have to figure out what size it's supposed to be. Yeah, so that's a little bit different. But there's not, if you change I at all, you'll find that you can find a matrix that it doesn't work for. Yeah. Okay, and so next time, now that we've got the matrix that's analogous to 1, next time we'll talk about what it means to have a multiplicative inverse. Right? So for numbers, right, sometimes you can have a number that you multiply by and get the multiplicative identity. Right? What about matrices? Well, sometimes it's also true. Sometimes you can find a matrix that when you multiply, you get the identity. That's called the inverse matrix. Okay. And so that's what we'll talk about next time. Okay. Okay. That's it for today.